Welcome back. Kind of part two of this. This is a lot less math. Hopefully, you followed along with the equations and the calculations and can see how to do the math. Just be very careful with your parentheses, with all the scientific notation. Um, please note that about the Learn Smart. Again, the Learn Smart's going to be about two. I'll give you 2 weeks for it. It's going to be. We've done about two-thirds of it so far. Um, Electric forces, electric fields, static electricity, that type of stuff. So it'll just be kind of ongoing in resources as well for you to reinforce it. Today's going to be looking more at that relationship that I kind of alluded to with the topographical maps and elevation and how we actually graph and give a visual representation of field lines. The nice thing about when you get a model, that's what this is with the field lines, is that we can look at. Let me go full screen here. Hold on. And I'll talk about the field lines. But what this is a field line model. It gives you a working model of what would happen if you put some kind of charge in this system. Um, and it's just like the topographical maps, so you can kind of get the lay of the land, pun intended there, of what it's going to do to any kind of charge that you put into this system. Okay. Again, these are all based off of this Q of this charge and what any, this is the external field that's being created. So any other charge, Q naught, Q1, Q2 that I put into this system, I have a way to predict what it's going to do. For those of you that were there for that day with the field hockey simulator, and I clicked on all those lines, that's what that was doing. It was mapping those field lines, and it was predicting what kind of force was going to be applied if you put a charge in that system. Please remember the arrows, it's a vector. The arrows always show the force that would be applied to a positive test charge in that system. All right. So some rules for drawing these, and kind of overall how these field forces or these field lines work. First one there, you see the lines must begin on a positive charge or at infinity and must terminate on a negative charge or at infinity. Okay. The number of field lines drawn leaving a positive charge or approaching a negative is proportional to the strength. So if you have double the amount of field lines, that's double the charge. If you have 3 times as many field lines, that charge is triple of what one would be. So say you have 2 field lines going from an object, and you looked at another example that had 6 field lines. The one that had 6 field lines is going to be 3 times as much charge that's producing that field. So it's proportional. And no 2 field lines will ever cross. Okay. Old school Ghostbusters here. Don't cross the streams. The beams, the lines, they cannot cross. They'll never cross. So here's a very excuse me, basic example here. Top one, you have this positive charge creating a field. How would a positive charge, if I put a charge in here and it was your positive test charge, it's going to be repelling. Now understand, if you put a negative, it's going to go opposite the field lines. Notice how the distribution, they're all evenly spaced because I have one charge. Over here, you have a negative charge setting up a field. By counting up the lines, they both have the same amount of lines, so they would both have the same charge, just opposites. Okay. The interesting thing now starts to come into play when you start putting different charges together and looking at the net field that's being produced. For those of you, again, that were there for that simulator, this is what you would see happening. You would see some of these happen. So if you put a positive charge in here, you would see it follow and it would go up and it would curve back down into this charge. Now, if you put a negative charge here, okay, it's going to zip right down into here. It's going to go opposite the field lines. If you put a positive test charge out in this area, it's going to fly out and not come back. So it's giving you a nice working model of the force that is going to be applied to any kind of charge that you put into this system. Now notice the distribution. You have a very almost what we call a uniform field right in this area. They're almost parallel. Later we'll get to how we can create parallel lines. But here you have you put a charge right here, it's going to shoot and zip right across there. Same amount of field lines entering and exiting, so these would be just equal but opposite. Okay. Here's what you would see if two positive charges would be applied. Again, they're going to move away from each other. Now, notice if I put any kind of charge in this area, there's no field lines. That charge is going to stay there. The net force on that object is zero, no change in motion. Now, here you can see that what I was talking about with the distribution of charge. The one on the left, the positive, is double it. So if you count those lines, they're going to have twice as many field lines as the one on the right. But still, you can still see what it would do if you put a charge in that system based on the field lines. All right, now here's where it kind of gets fun and interesting here, and it's going to explain a lot of things as we go forward. Okay. A conductor, a metallic object, an object that can allow charge to move. The electric field is zero everywhere inside the conductor. Now, that's interesting. So, you know me and my drawing. Let's say you have your car. Okay. In essence, it's a box of, well, it used to be at least of metal. That charge is going to remain on the outside of this object. So if it gets hit by lightning, okay, that charge is going to remain on the outside. You can physically touch the inside of that metal door and you're not going to get electrocuted because that charge is going to remain on the outside. You're safe in a car not because of the grounding of the rubber tires, but because that charge remains on the outside. It's called the Faraday Cage experiment, or the Faraday Cage. A Faraday cage, if you've ever seen them do the science experiments with the huge zapping lightning going every which way, I'll have to see if I can find a video and post it for you. But you will see them inside of basically a steel mesh cage. That that is the reasoning. All that charge that's hitting that cage stays on the outside and they're protected. This is why when you go to, say, a big warehouse, you don't get any cell signal. You go to the mall or sometimes Walmart's or Sam's Club that has all metal structure, it's hard to get signal inside. Well, that cell signal is a charge, it's electrical signal. It stays on the outside of that building and can't penetrate. Um, a lot of labs, government labs doing a lot of research labs, they will actually embed chicken wire in the walls and ceiling so that no signals can get in or out. So it creates almost a safety chamber. So that's the Faraday effect. Any excess charge on an isolated conductor resides entirely on the conductor's outer surface. That's what we're talking about here. The electric field just outside a charged conductor is perpendicular to the conductor surface. Okay, so if you looked at the electric field here, it's going to be exactly perpendicular to this surface everywhere, just at that instant in time, that instant in place. And on an irregular shaped object, so curves, points like lightning rods, charge tends to accumulate where the radius of curvature of the surface is the smallest. In other words, at its sharpest point. Okay, and I got a diagram here. I believe I'll show you here. So if you imagine a lightning rod, and over here is the point or a pointy object or the top of your umbrella. Okay, the charges are a lot closer, and if you remember that R squared value, that electric field strength is a whole lot stronger here. So if lightning is attracted to an opposite charge, lightning comes in, where's it going to hit? The point. And so that's why you have these lightning rods up at its highest point. You have that pointed rod. It creates kind of a beacon. It says, strike me here because I have the biggest attraction to you versus the roof or the pitch of the roof. So let's look here. So we're going to use that diagram that I flashed. The electric field lines for 2-point charges separated by a small distance. Determine the ratio of Q1 to Q2. Okay. Well, Q1 to Q2. So if I count up here Q1, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3, 4, 5, 6, 7, 8, 9. Okay. So I have 9 lines leaving. Up here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. So I got 24 lines here. Again, I got going cross-eyed here, 9. Okay. So it's a 9 to 24 ratio. Okay, so that's telling you that Q2 is quite a bit stronger. Okay. Not quite 3 times the strength, but almost. So let's go back to rubbing your feet on the floor, okay, and shocking somebody. Why do you see the discharge? And you always, when you go to shock your, sibling, point your finger and you don't put a palm out. Okay. Well, you're rubbing your feet on the floor. You're building up that charge in your body. You have a net negative charge. They don't like to be by each other. They're going to find a way out. Well, remember, they accumulate in the strongest field at a point. So if you point your finger, you have a strong field at that location, just like the lightning rod. And if you get it close to something else, that's where it's going to discharge it. If you try to put a palm or your fist, the charges are too spread out. You don't have a strong enough field to create that force for those charges to jump. Okay. Again, that'll kind of wrap up field force or fields, identifying them, looking at how they work, doing the calculations of how, and now we're going to start kind of transitioning to, all right, I have this static charge. I have this force buildup. In other words, I have like a rubber band stretched. Now, what happens when I release that rubber band? What happens when I now allow charge to start moving or flowing? Okay, so that's going to be kind of the next phase as we go forward. Again, any questions, please communicate with me. If we need to have some meetups, let's do it. Just make sure you're contacting me through email or through classroom. Emails the easier way for me to respond to you. But just please keep in touch. Please be working through your Learn Smart. Again, you got about 2 weeks to do that. Um, and the next lesson, we'll start looking at this charge actually starting to move and get into electricity and then voltage, current, circuits, the types of things that actually charge flowing instead of just being static.